Okay, everyone, welcome back. Now recording is in progress. So let me just continue about the topics that we have not finished today about the simplex algorithm. And I will use the examples that I have shared with you in our section to tell you the details about how to execute the simplex algorithm. So let me write down the examples that I have said. So our objective is to minimize negative y1 minus y2 minus y3, and the constraint is y1 plus 5y2 plus 4y3. Now I will just add our slack variable onto the constraint. Okay, so the second is 3y1 plus 2y2 plus 6y3 plus y5. This is 0, and 5y1 plus 4y2 plus 2y3 plus y6. This is, sorry, the right hand side I should write 1, and 2y1 plus 6y2 plus 3y3. This, and add y7. This is 1, and also y1 to y7. They should all be non-negative. All right, so this is what we do for simplex algorithm. First, we construct this so-called coefficient matrix. And the coefficient matrix is just to take out the coefficients of all the constraints and also the coefficients of our objective function. So let's see our constraint. The first constraint, the coefficient is 1, 5, 4, 1, 0, 0, 0. And the second, and on the right hand side is 1. And the second constraint is 3, 2, 6, 0, 1, 0, 0. And right hand side is 1. So let's just finish writing them. 2, 6, 3, 0, 0, 0, 1, and 1. So to separate the constraints and the objective function, so we draw a horizontal line here. Okay, 0, 0, 0, 0. So what does this tell us? This tells us that the coefficients in the objective function is -1, -1, -1 for y1, y2, and y3. And for y4, y5, y6, and y7, they are 0. Okay, so now the value of our objective function is 0. Why? Because, so if you look at this coefficient matrix, we see that here, this is an identity matrix. So that's to say, now our y4, y5, y6, y7 are basic variables. We call them basic variables. Okay, so let me write down y4, y5, y6, y7 are basic variables. Why? Because for their corresponding column, there is only 1, 1, and this one is the pivot 1. So y1, y2, y3, now they are non-basic variables. They are non-basic variables. So for non-basic variables, I need to write here. Basic variables are non-zero, while non-basic variables are 0. So we see that here our y1, y2, y3 are non-basic variables. So now the value of y1, y2, y3 are 0. And according to what we have discussed in our section today, we see that, so now 0, 0, 0, these are for y1, y2, y3, and 1, 1, 1, 1. These are the values for y4 to y7. And this is a vertex of our feasible region. So when we execute the simplex algorithm, essentially we are just traversing the vertices of this convex hull. The convex hull is actually the feasible region until we find the optimal vertex. Okay, so now in the following steps, every time what we need to do is to choose some non-basic variable to be a basic variable, and also choose a basic variable to be the non-basic variable. So in our case, actually every time, in every step, we should have 4 basic variables, and the remainings are non-basic variables. So that's to say, we need to choose a non-basic variable to be the basic variable. The way is to look at this. So the method is to choose the most negative coefficient to enter the basic variable. Right. So what does this tell us? Why do we need to choose the most negative coefficient to enter the basic variables? Because we know that all the variables should be non-negative, right? So if we choose the most negative coefficient, that's to say, if we go along the direction of this variable, we make this non-basic variable to be a basic variable. That's to say, we can increase it from 0 to some value which is greater than 0. And if we choose the most negative coefficients, that's to say, this can make our objective function decrease in the fastest speed, right? Because we know that our objective function is linear. It's linear, so that's to say we need to choose the most negative coefficient and then to change this variable from non-basic to basic. Okay, let me also write here. This is our value of objective function. All right, so then, as I said, we have to choose one non-basic variable to be a basic variable, and we see that here they are -1, -1, -1. So we can just feel free to pick any non-basic variable to be a basic variable. So let's say we pick this guy. We pick x1 to be a basic variable. Then our next step is to look at this column and this column, because as I said, we need to make a basic variable to be a non-basic variable. So what we do is to let me write down here. We need to swap a basic variable with a non-basic variable. Okay, and the way to pick a basic variable and make it the non-basic variable is that we need to look at the number in yellow, as I have highlighted, because we have picked x1 and we want it to be basic. So we look at so the yellow one is the first column. It's the column related to x1 in yellow and green column. And the trick here is to choose the smallest positive ratio of green over yellow. And we want this to leave the basis. That's to say, we want this one to be a non-basic variable. So let's see, what are the ratios? So we see that the ratios are 1/1, 1/3, 1/5, and 1/2. What is the smallest positive ratio? This guy, right? So that's to say we need to swap y1 and y6, right? Because if you look at this row, the leading the column with the pivot 1 is here, and this corresponds to y6. So that's to say we want y6 to leave the basis and to be a non-basic variable. Okay, so how do we make y1 to be basic while y6 to be non-basic? We need to do elementary row operations to the matrix such that the column for y1 has only one pivot 1, while the others are 0. And also, oh yeah, so just to make this, because in linear algebra, you know that if we do elementary row operation, we want column 1 to only have only one leading entry, and then it means that y1 becomes a basic variable. So the resulting matrix is like this: 0, 21/5, 18/5, 1, 0, -1/5, 0, and this is 4/5, 0, -2/5, 24/5, 0, 1, -3/5, 0, and 2/5. Okay, so I hope that I think that I have calculated correctly. Okay, so after we do the elementary row operation, we see that now y1, y4, y5, and y7, these are the new set of basic variables. So that's to say now our basic variables are y1, y4, y5, and y7. Right, so these are the basic variables now. And we can also say that here, 4/5, this corresponds to y4, because the leading one is here. And for the y2, y3, and y6, they are all 0 because they are non-basic variables. So that's to say now we have come to a new vertex. On this new vertex, y1, y4, y5, y7 are non-zero, while the others are 0. So y4 has value 4/5, and y5 it has value 2/5, and y1 it has value 1/5, and the remaining is y7. It has value 3/5, and the value of our objective function is 1/5. You can just check it, because it is minus y1, right? And the coefficients of Yeah, this is so it is 1/5, and then we need to we need to repeat. That's to say, we pick the most negative coefficient in the bottom row. and compute the smallest positive ratio. And then we switch the basic variable and non-basic variable and do elementary row operation. This is elementary row operation. And we also need to compute the value of objective function. Right. So let me just write the answers in the following step. So you see now, we need to choose -3/5 because this is the most -3/5. This guy is the most negative coefficient in the bottom row, right? So that's to say we need to make y3 to enter the basis. So we choose this. Oh, we choose y3 to enter the basis, and we also compute the ratio. And by repeating these steps, what we obtain, let me see, is 0, 9/2, 0, 1, -3/4, 1/4, 0. And the bottom row is okay. So we have arrived here. Then let's look at the bottom row again. Now, -1/4 is the only negative value in the bottom row. So of course we need to pick y2 to become a basis, and we do the green one, and we also compute the ratio. The ratio, remember, it is green over yellow. Okay, so then what we obtain is 0, 0, 0, 1 -3/10, 41/110. Yeah, sorry for my handwriting. So we see, so we can see that now for all those non-basic variables, let me change your color. So now these guys are the non-basic variables, and what do we observe? We observe that their coefficients are all positive. Then we can stop. Why? Because the coefficients of non-basic variables are all positive. What does this mean? This means that you have already arrived at some vertex. Let's say now you are at this vertex V. And then wherever you go to any adjacent vertex, the value of the objective function should always increase because the coefficients of these non-basic variables are all positive. That's to say, if you want to make a non-basic variable to be a basic variable, you need to increase the value of this non-basic variable to be positive. However, because the coefficients of these non-basic variables are all positive, that's to say, in this process, the value of your objective function must increase. So because the value of your objective function must increase, that's to say, now your V is the optimal solution. And as I have emphasized in our class today, for this minimizing C transpose X such that AX equals to B with X greater than or equal to 0, what can we say? Our objective function is convex, right? This can be checked by the definition of a convex function. And also, feasible region is also convex. So that's to say, whenever you arrive at a point such that for any points in its neighborhood, the value of the objective function increases, then you can conclude that you have already arrived at a global minimum point. And if we review this process of simplex algorithm, we see that every time we make a non-basic variable to be a basic variable, and accordingly, a basic variable to be a non-basic variable. That's to say, every time we just change from one coordinate, or say we just change one variable from non-zero to 0, and another variable from 0 to non-zero. So graphically, what does this mean? Graphically, it means that, so suppose now you're at some point, say X, okay? And because you just swap two variables and the other variables do not change, that's to say, what you are doing is actually, this is the feasible region, and this is one vertex, this is where you are now. You just swap one pair of basic and non-basic variable. That's to say, you just walk in some direction such that you will arrive at a new vertex. And this new vertex with X, they are adjacent to each other on this convex set, on this feasible region. So that's to say, the simplex algorithm, what it essentially does is just to traverse the vertex of this feasible region until you arrive somewhere such that you no longer be able to improve the value of the objective function, and then you can stop. And because of convexity, this is just like you are walking on a mountain with your eyes closed. And every time, what you need to do is just to find the direction that helps you to descent the most. This is the steepest descent technique. You just go the direction with the steepest descent, or say with the slope that is negative, and it has the maximum absolute value. So in this way, once you arrive at some point such that you can no longer improve, then you are done. And in convex optimization, we call this deepest descent method. And in general, if some function f, this is our objective function, it maps from Rn to R. Let's say fx, where x is in Rn. Then the steepest direction is just the negative of the gradient of fx. And this gradient of fx is actually negative partial f, partial x1 up to partial f, partial xn. So that's to say for the steepest descent method, and here our simplex algorithm, their cores are the same. So I hope after my talk, you will understand the reason why we use simplex algorithm and the rationale behind it, why simplex algorithm makes sense. And I can say that simplex algorithm is very useful in operations research. It was developed by, we can say that he's the father, the inventor of simplex algorithm is the father of operations research. His name is George B. Dantzig, who was a professor in Stanford University before his death. Okay, so I think I have finished the contents for simplex algorithm. So see you in the next section.